Hello, this is Joe Trout from the physics program at Stockton University. We wanted to talk a little bit about Hubble's constant, but in order to do that, we needed to discuss galaxies a little bit. So let's start with that. So if we look at a galaxy, that's a collection of stellar and interstellar matter, and it contains stars and gas and dust and neutron stars and black holes. And it's isolated in space and it's held together by gravity. And there's billions beyond our galaxy. And our galaxy is known as the Milky Way. And if we look at the center of the galaxy, our sun is about 28,000 light years away from the center of our galaxy. And there's this disk that we talk about and this nuclear bulge. And the angle of about 60 degrees, there's an angle of about 60 degrees to the celestial equator. So it's tilted a little bit. And our galaxy is called a spiral galaxy. And here's two other spiral galaxies, one viewed from the side. So here we're looking at it on edge, and the other looked at from the top. And we call these spiral galaxies because these arms of stars and dust that spiral out from the center. And if you look at it from the side, you'll see that there's this like little bulge here. So this is the first one is M101, and this is out of the Meissner catalog of astronomical objects. And there's also the new general catalog, and this is NCG 4565. So as seen from the Earth, we see a few stars when we looking out of the galaxy. If we look at if we look at in the directions of these red arrows, and we see many stars if we look in the direction of the white arrow and the direction of the blue arrow. So here's a picture. If you go to a really dark location, you can see the Milky Way stretch across the sky. Even here sometimes, and if conditions are just perfect, you can get an idea of where the Milky Way is. And it's just this line of stars and dust and everything that stretches out across the sky. If we look in the infrared, this shows an infrared view of our galaxy, and it shows much more detail than the visible light view does. And the infrared is not as absorbed as much by the gas and the dust of the galaxy. So when we talk about the galaxy, we usually talk about the disk, the bulge, and the halo. And in the halo, there's essentially no gas or dust. And in the disk and the bulge, there's interstellar material, there's gas and dust, and this can be used to create new stars. There's also a clear difference in color between the disk, bulge, and halo. So the bulge and the halo are redder than the disk. And there's a gas-rich galactic disk is the site where we have ongoing star formation happening, and it contains stars of all ages. There's also a galactic halo where there's old stars and there's no new stars forming. So here we see the nuclear bulge, right? And the galactic nuclei and nucleus. And here's the disk as it spirals out. And here's some globule clusters in the halo. And In the disk, its diameter is about 100,000 light years across, and it has spiral arms, and there's younger stars and stars forming in these disks. And the halo, it's very large, right? That's all this stuff out here. And there's a spherical distribution of older stars. So in the galactic halo and the cluster, in the galactic globular clusters, form very early. And the halo is essentially spherical. And all the stars in the halo are very old, and there's no gas or dust. And so it's not surprising that the stars are all very old because there's no gas or dust for new stars to form. And in the galactic disk is where the youngest stars are, as well as the star formation region, right? So we have emission nebula and large clouds of gas and dust. And they're surrounding the galactic center and the galactic bulge, which contains a mix of older stars and younger stars. So there's stellar orbits in the disks of the planes, and the stars move around like this, and they're all in the same direction, and they orbit in the halo and the bulge are much more random. So how can we talk about the distances? Why do we know how big, for instance, the Milky Way is, right? And there's two ways. There's variable stars and there's radio mapping. So if we look on the HR diagram, the variable stars are on the HR diagram, and there's a pulsating variable stars lie in this instability strip, right? And the high mass stars evolve as Cepheid variables, and the low mass stars as RLL Leray variables, variable stars. So you can see they're pretty bright, right? So they're at least 100 times the brightness of the Earth. Because if you remember, we called the Earth 1 and its temperature was 600. And it's a star G, it's a class G star. So it's about 100 times to 10,000 times brighter than our sun. And the high mass stars evolve into Cepheid variable stars, and the low mass stars into RR Leray stars. So don't forget, what holds the star together is that gravity's pulling in and pressure's pushing out. And they're usually in balance. Like for in our sun right now, it's in balance. And our sun stays pretty much the same size. So the pressure force pushing out equals the gravitational force that's trying to pull in. And the star expands and cools. And so when a star compresses, it heats up and pushes out on the outer layers. And when a star expands, it cools and contracts. So for these variable stars, it keeps repeating. It'll compress and heat up and push out, and then it'll push out and cool off and then contract, and it'll go back and forth like this. And the cycle keeps repeating. So these low mass variable stars have periods shorter than a day, and the high mass variable stars have longer periods. Normal stars that experience a brief few million years periods of instability. So these will move back and forth and grow and shrink, and they become variable. So the upper plot shows an RR Leray star, and all the stars have essentially the same period, about half a day to a day. Don't forget, the period is the time for it to repeat once. So what happens is this star gets bright, and then it dims down, and it gets bright, and then it dims down. And in this case, right, the period is right really close to 1 day. So the upper part is for our Lorraine star, and the period is about 1 day. And for the Cepheid variable, they can range from 1 day to 100 days. So the time for it to get bright and dark and bright again could be 1 day, or it could go up all the way to 100 days. So the usefulness of these stars comes from their period luminosity relationship. So it's really easy to measure the period, right? We just look and it gets bright and it gets dim and it gets bright and it gets dim. And we can see how long it takes for that to happen. But we'll also look at the luminosity. So don't forget, this luminosity is in solar units. So for instance, these RLR Lorraine stars are about 100 times, right, the brightness of our sun. And for the Cepheid variables, they go from about 100 times to about 10,000 times the brightness of our sun. So we can get distances from these variable stars, and this is how we do it. We'll get the distance of a variable star. We'll measure its apparent brightness. So don't forget, we can tell that um, um, if we look from Earth, we see the apparent brightness. So for example, there could be two stars that look about the same brightness, but really one of those stars is much further away and it's brighter. But when we look up at the sky, we can't tell that. So what we do is we measure their apparent brightness, their apparent magnitude, and then we measure its period. And we use this period luminosity relationship to determine its absolute magnitude. And from this, we can use this relationship between the apparent magnitude and the luminosity. So we're talking about the apparent brightness to its actual brightness to determine the distance. So for RR Lorraine stars, they all have about the same luminosity. So knowing their apparent magnitude allows us to calculate the distance. Cepheid variables have a luminosity that's strongly correlated with the period of their oscillation. So once the period is measured, the luminosity is known and we can proceed as above. So this is what we've decided. As we look at the brightness coming off a star, and as the light moves out, it spreads out over a larger distance, right? Over a larger area, excuse me. An area is just a distance squared. So our apparent brightness comes out to be the luminosity divided by the distance squared. So if I want to know the distance, it's just equal to the square root of the luminosity divided by its apparent brightness. By the way, we can also use radio waves. So we have radio waves can penetrate clouds of dust and gas, and the dust and gas absorb light at a specific wavelength, about 21 centimeters. So if clouds are moving, the Doppler shifts causes absorption to be shifted, so we can see more than one set of clouds. So for example, if we look down at this line of sight and we're watching these, right? And here's stars that are moving in that direction and in that direction and this direction, we can tell how that's working using radio mapping. So here we see, using radio mapping, what our spiral galaxy that we live in looks like. So our spiral galaxy has four major arms and some short arms. And the sun is in a shorter arm called the Orion arm. The major arm of our spiral galaxy is the Sagittarius arm, and that's towards the galactic center. The Perseus arm, away from the galaxy center. Centaurus arm and Cygnus arm. So why is the galaxy in a spiral shape, right? So we don't think it's that the galaxy is rotating at different speeds and winding up, right? So if the galaxy rotated as a solid disk, what would happen is it would just keep moving like this. But if the galaxy rotated at different speeds, what would happen is those spiral arms would start to bend. I'm sorry, those radial arms would start to bend. So here's a group of stars, and here's a group of stars, here's a group of stars. And if the galaxy was all rotating as a solid disk, and I mean all of the ones in the center were moving at the same speed, and all the green ones at the same speed, and all the red ones at the same speed, then it would look like this. However, if they were moving at different speeds, what would happen is the spiral arms would start to appear. So, somewhat surprisingly, that we even see spiral arms since the galaxy does not rotate as a solid body. But after a few rotations, the spiral pattern would be wound up very tightly, as shown in the diagram. And this is known as the winding dilemma. So if the spiral arms cannot rotate along with the galaxy, they would curl up, so they would all become really tight little curls. Rather, they actually appear to be density waves. So instead, what happens is that stars move in and out of the wave, much as a traffic jam would. So here's the idea. Let's say you're driving down and it's pretty busy on the expressway, and there's lots of cars and they're all going 65 miles an hour. And suddenly this car slows down. That causes this car to slow down. And then it causes this car to slow down. Then let's say you go around a barrier or something, and now car one speeds up. But it's going to take a couple of seconds at least for car two to react and start to speed up again. So what we see is that as these cars move through this little traffic jam, right, the lead car is going to take off, and then the car that is moving in is going to slow down and get caught in the traffic jam. So we think spiral galaxies work this way. So there's an alternate theory that the formation of stars drive the density waves. So in this case, you can imagine a row of newly formed massive stars somewhere in the disk. And the emission nebula created when these stars form, and the supernova when they die, sends shock waves through the surrounding gas. And this possibly triggers new star formation. And the formation of one group of stars provide a mechanism for the creation of more stars. So some of the computer simulations suggest that this is correct. But for now, this idea of this traffic jam at least has gives you a visual picture of how these how these spiral arms form. We also see these globular clusters are located and spherically distributed through the halo. And if we look for these variable stars, they tell you the distance. So once again, we said we could find the distance by looking at the square root of their actual brightness, their luminosity, over their apparent brightness, what we see from Earth. If we wanted to find the galactic center, and we're not in the center of the galaxy, right? So how do we find it? We locate globular clusters in the halo, and then we determine the distance to these globular clusters, and then using variable stars in the cluster. And then we can find the center of the globular cluster distribution, and that is the galactic center. So our sun is about 8.6 kiloparsecs from the center of the galaxy. We can also find out the rotation speed. We can measure the rotation speed and the distance from the galaxy, right? And this is based mostly off of radio data. So here's our galactic sun center. The sun's moving around in one of the arms of the galaxy, and we have this galactic disk. And we can see there's kind of a tilt, right? There's an angle at which it lies. So let's say we're looking at a star, and let's say we look at the light from the star, and all of a sudden something comes and gets in the way. Sometimes we can still see the star, because what happens is we get this gravitational lensing, and actually the star will look brighter, right? And then it'll go back to looking normal. So as this happens, and we'll talk more about this when we talk about curved space, but we can see that this light is affected by the gravity. And even though we shouldn't be able to see the star, light that was going out this way gets bent around the star, and we can still around the object, and we can still see the star. So here shows some pictures of the galactic center. So here shows a couple of different radio and X-ray and infrared images of the galactic center. So what do we know about the galactic center? Galactic center appears to have a stellar density about 1 million times higher than the Earth, right? So there's a whole bunch of stars in there. And there's a ring of molecular gas about 400 parsecs across, and it has strong magnetic fields and a rotating disk or ring or disk of matter a few parsecs across, and a strong X-ray source. We also think that there's a black hole somewhere near the center of our galaxy. So these stars are very close to the galactic center, and their orbit is just about a right fit. So it assumes that there's a center of a black hole of about 3.7 million solar masses. So we have this black hole that everything seems to be rotating around. And many of the galaxies have a black hole. So here's the idea. We can find the distance from variable stars. So we go ahead and look at a variable star, and try to figure out where it is. So in 1912, we discovers the Cepheid period luminosity relationship. So bright Cepheids pulsate slowly, and dim Cepheids pulsate quickly. So if we look at the luminosity, and these are in, solar magnitudes. So this is 100 times the brightness of the sun, 1,000 times the brightness of the sun. And here shows their period. And we see that um, that the bright Cepheids seem to pulsate slowly, and the dim Cepheids pulsate quickly. So this is an artist's conception of the various parts of our galaxy and the position in relation to our sun. And we have these galactic spiral arms, and as clouds of dust, gas and dust move through these spiral arms, the increasing density triggers star formations, right? And this may contribute to the propagation of the arms. So if we look face on, this is what we expect it looks like. And here it is edge on. We also have a sister galaxy, and this is Andromeda. So spiral galaxies are classified according to the size of their central bulge and the tightness of the arm. So for instance, for spirals, we have SA and SB and SC. And in this case, SA, there's a big nuclear bulge, and SC, there's a small one. And for SA, the arms are tightly wound, and for SC, they're loosely wound. So here's some pictures. SA, tightly wound, and SC, loosely wound, right? This has a big bulge, and this has a much smaller bulge. This shows the same thing edge on. We also have things called barred spiral galaxies. And these are like spiral galaxies, except there appears this bar in the center. So we said these spiral galaxies form because of the spiral arms are like traffic jams. So the jams are always there, but the cars move through them. And we think that the stars do the same thing in the arms of these spiral galaxies. So for instance, here, a truck was moving slowly in this lane, and that slowed everybody else down, right? But as people go and pass the truck, they speed up and move away. But cars keep coming to fill in this traffic jam. So that's what we think how galaxies work. There's also elliptical galaxies, and they have no spiral arms and no disk. And they come in many sizes, and from giants with trillions of stars down to dwarf ellipticals with just a few million stars. They also contain very little, if any, cool gas or dust, and they don't show any evidence of ongoing star formation. So the elliptical galaxies start with E0, they're perfectly round, and go to E7, which are really elongated. So here shows some pictures of the elliptical galaxies. So this is an elliptical galaxy, but there's so few stars that it's almost hard to tell that this is actually a galaxy. So we also see that these galaxies have disks and bulges, but no spiral arms and no interstellar gas. So there's no star formation going on. And we have irregular galaxies, right? These might occur because you have two galaxies that collide together, and then you're left with kind of a mess, right? So that's possible what's going on here. So here shows a couple more of these irregular galaxies. So a guy named Hubble was looking at these and categorizing them. And what he thought originally was that these kind of develop into these other galaxies. That's not thought so much anymore, but we still use this idea of this tuning fork, right? So here's elliptical galaxies, perfectly round and really elliptical. And then we have the spiral galaxies and the spiral barred galaxies. So the Hubble classification, we had spirals, we had bars, we had ellipticals, and we had irregular galaxies. And we said now we can see how far away the galaxy are by looking at their Cepheid variables. So what we'll do is look at the luminosity and look at the period. And from there, we can figure out how far these galaxies are away. So Edwin Hubble discovered the Cepheids in the Andromeda nebula M31, and it's about 2.2 million light years beyond our Milky Way. If we look at our local group as a cluster of galaxies to which the Milky Way belongs, and our local group is relatively poor, it only has about 40 galaxies. Andromeda M31 is the largest and most massive. More than a third are dwarf ellipticals, and about three are spirals, and there's new dwarf ellipticals being discovered. So our nearby galaxy cluster, the Virgo cluster, is much larger than our local group, and it contains about 3,500 galaxies. So the most galaxies are too far away to pick out Cepheid variables, and their distances are found using Doppler shifts instead. So all the galaxies seem to be moving away from us with the redshift of their motion correlated with their distance. So the vertical arrows in each spectrum highlights a particular feature and a pair of dark absorption lines of interest. And the horizontal lines indicate how this feature shifts to longer wavelengths in the spectral more distant galaxies. So here's what Hubble showed. Hubble looked at the recession velocity in kilometers per second and looked at the distance in millions of parsecs. And so he plotted all of these, all of the galaxies that he could, and he looked at their recession velocity, which he could tell from the redshifts, and he looked at the distance, and he could tell that from the variable stars. So he found out that the relationship, the slope of the line is so this is a straight line, and if it's a straight line, it has a slope, and He called this slope the Hubble constant. So what he said was that the recession velocity is equal to HO times the distance. So this is like y equals mx plus b, where b is 0. So the value of the Hubble's constant is currently uncertain, but most of the estimates are 50 to 80 kilometers per second per megaparsec. So the things that we can use to find distances are we can use light, and we can use uh, the star brightness, and we can use the Cepheid variables and other things, and then all the way up to the Hubble's law, where we look at the velocity versus the distance. So here's what we think happened. We get these young stars, and there's a bunch of dust and gas, and they start to rotate. And we see that the gas and dust fall into a plane, and we start to see our galaxies being formed. So next week, we'll talk more about this Hubble constant and what it means and how it can be used to look at the age of the universe.